Hello, in this video I'd like to talk about limiting reactant stoichiometry problems, continuing our unit on stoichiometry calculations. As we learned in the first part of this unit, every stoichiometry problem begins with a balanced chemical equation. And in this case we'll use our hypothetical equation, 2a plus b reacts to form 3c. In the first part of this unit we covered ideal stoichiometry. And in an ideal stoichiometry problem, we ask the questions: if I give you an initial amount of A, how much B do we need to use it all up? And how much C do we expect to get out? We also ask the question, for a desired amount of C that I want to end up with, how much of reactants A and B do I need? Why is this called an ideal stoichiometry problem? Well, because everything is used up and nothing is left over. Now, in this section, we're going to deal with limiting reactant stoichiometry problems, which also start with a balanced chemical equation. Now, in this type of problem, we ask a slightly different question. If I specify initial amounts of both reactants A and B, which reactant is the limiting reactant? And the limiting reactant is defined as the one that is used up first and therefore controls the yield of the reaction. That is, it controls how much product you get. The next question is, which reactant is present in excess? Well, it's going to be the other one, the one that's not the limiting reactant. What is the theoretical yield of the reaction, which is defined as the amount of product we expect to get, and what mass of excess reactant is left over? So, let's begin with an example from the kitchen, a grilled cheese sandwich. That looks good. To make a grilled cheese sandwich, you need 1 piece of cheese and 2 slices of bread. So suppose I go into my kitchen and I see that I've got 15 pieces of cheese and I've got 20 slices of bread, and I want to know what's the maximum number of sandwiches that I can make. Well, one of the 2 ingredients is going to be the limiting ingredient. That is, it will control how many sandwiches I can make, and one of them is going to be left over. Now, what I can do is predict how many grilled cheese sandwiches I can make starting with cheese and how many grilled cheese sandwiches I can make starting with bread, and then compare them. So, if I start with cheese, well, I said I had 15 slices of cheese times 1 sandwich per 1 slice of cheese. Means I could possibly get 15 sandwiches. But if I start with bread, 20 slices of bread times 1 sandwich per 2 slices of bread, that's only 10 sandwiches. So if I want to use up all 15 slices of cheese, I could get 15 sandwiches. But if I want to use all 20 slices of bread, I can only get 10 sandwiches, which is correct. Obviously, the smaller number of sandwiches, which in this case is 10, and therefore bread is the limiting reactant. It gets used up first, it limits how many sandwiches I can get, and it also controls how much of the cheese, which was the excess ingredient, gets used up and then is left over. If this makes sense to you, then it will also make sense when we apply it to a chemical reaction. So let's do that. In this hypothetical reaction, aluminum reacts with fluorine to form aluminum fluoride. There is our balanced chemical equation. If I react 10.0 grams of aluminum and 25.0 grams of fluorine, here are our questions. Number 1, which of these is the limiting reactant and which one is present in excess? What is the theoretical yield of reaction, which we said is defined as the mass of product expected based on your stoichiometric calculations? What mass of the excess reactant will be left over? And in order to do these calculations, of course, we're going to need the molar masses. So let's calculate our molar masses. Aluminum from the periodic table has a molar mass of 26.98 grams per mole. For fluorine, we'll do 2 times the molar mass of fluorine to give me 38.00 grams per mole. And for aluminum fluoride, I'll take the molar mass of aluminum plus 3 times the molar mass of fluorine to give me, check my calculator really quickly, 83.98 grams per mole. So let's begin the problem. Okay. Now, the issue is, how do we determine the limiting reactant and the theoretical yield? Now, there are a number of different ways to solve a problem like this, and I've decided this year I'm going to teach you what I think is the most obvious one. If you want to do some research and find other ways of solving this problem, that's perfectly fine with me. What we're going to do, just like we did in the cheese sandwich example, is to calculate the theoretical yield twice. Once starting with aluminum and once starting with fluorine. We will get 2 results. Which of the 2 results is correct? Obviously, it will be the smaller one. Whichever of the 2 reactants predicts a lower theoretical yield must be the one that gets used up first and therefore is the limiting reactant. And the theoretical yield you calculate starting with that reactant will be the correct one. So let's demonstrate. Okay? So I'm going to begin by calculating the theoretical yield starting with 10.0 grams of aluminum. 10.0 grams of aluminum divided by the molar mass gives me moles of aluminum. I'll multiply that by 2 moles of product, aluminum fluoride, for every 2 moles of aluminum. And I'll convert that to mass by multiplying by the molar mass of aluminum fluoride. And that gives me 31.2 grams of aluminum fluoride. So if aluminum is the limiting reactant and therefore gets used up first, I'll expect 31.2 grams of aluminum fluoride. Let's do the same calculation, except now we'll start with the mass of the other reactant, 25.0 grams of fluorine. I'll convert that to moles by dividing by its molar mass. I'll multiply by the mole ratio, 2 moles of aluminum fluoride for every 3 moles of fluorine, and convert that to mass. That gives me 36.8 grams of aluminum fluoride. So, if aluminum is the limiting reactant, I'll get 31.2 grams of product. If fluorine is the limiting reactant, I will get 36.8 grams of product. They can't both be correct. Which one is correct? Obviously, the smaller one is correct. So, I'll put a box around the 31.2 grams of aluminum fluoride. I will label that as the correct theoretical yield. I will go back and now indicate that my 10.0 grams of aluminum represent the limiting reactant, and my 25.0 grams of fluorine are the reactant that is present in excess. Okay, so there's the first part. Now, the second part is how much of the excess reactant fluorine is left. Well, there's my balanced equation again. Well, this raises the question, what controls how much of the fluorine I started with actually undergoes reaction? Well, it's the limiting reactant. The limiting reactant controls everything. So, to figure out how much fluorine is left over, I'm going to have to calculate how much reacted and then subtract that from the mass of fluorine I started with. So, the mass of fluorine reacted, I'll simply do a stoichiometric calculation, starting again with the mass of aluminum, the limiting reactant. I'll convert that to moles by dividing by its molar mass. Now I'll multiply by the mole ratio, 3 moles of fluorine, the excess reactant, for every 2 moles of aluminum, and convert that to mass by multiplying by the molar mass of fluorine. That gives me 21.1 grams of fluorine that actually reacted. And now to calculate the mass of fluorine left over, it's very simple. I simply take the 25.0 grams of fluorine I started with, subtract the 21.1 grams of fluorine that reacted, and that gives me 3.9 grams of fluorine that are left over at the end of the reaction. Now, in this case, I can check my work by using conservation of mass as we've done before. I started out with 10.0 grams of fluorine and 25.0 grams 10.0 grams of aluminum and 25.0 grams of fluorine, so 35.0 grams total. At the end of the day, I calculated a theoretical yield of 31.2 grams of aluminum fluoride and 3.9 grams of fluorine left over that were present in excess to give me 35.1 grams total, which is approximately equal given rounding, so my calculations work out. Now, suppose in a real-life experiment, I only isolated 28.3 grams of aluminum fluoride. This is what's known as the actual yield. The actual yield is defined as the mass of product that the chemist actually isolates in the experiment. It turns out that most of the time, the actual yield is less than the theoretical yield. Well, why would that be? Lots of different reasons. I can describe this in more detail in class. It could be experimental error. It could be side reactions. It could be the product decomposes, or lots of different reasons. In any case, we're going to express the efficiency of the reaction by calculating what's called the percent yield. The percent yield of a reaction is not the same as the percent error in a measurement. The definition of percent yield is the actual yield divided by the theoretical yield times 100. So it's what you actually got in the laboratory expressed as a percentage of what you should have gotten based on your stoichiometric calculation. And you can do this for any stoichiometry problem. So in this case, to calculate our percent yield, we actually got 28.3 grams. We expected 31.2 grams. These are measurements, so they have significant figures, and that gives me a percent yield of 90.7%, which is generally considered to be pretty good. So, to summarize, given a balanced chemical equation, and when you are provided the initial masses of both reactants, you should be able to identify the limiting reactant and the excess reactant, calculate the theoretical yield based on the limiting reactant, calculate the mass of the excess reactant left over, and then finally calculate the percent yield given the actual yield. That's pretty much it. See you in class.